I'll add this to the recording because it's just worth discussion. We in that homework problem, we eliminated rows and columns 1 and 4, and we kept columns 2, 3, and 5, right? If I had more time, we would discuss all sorts of oodles of things about matrix analysis, because there's all sorts of related topics to what you're talking about. Like, for example, one of the strategies that internal computer programs will do, like they'll do internally, is they'll number it internally so that all the fixed boundary conditions are numbered last. And then all they do is they strike out all the rows and columns at the end, instead of what we did where we struck out like rows 1 and 4 and then columns 1 and 4 and then kept 2, 3, and 5. But it's just, you know, it's like we only have a little bit of time. What my main purpose on the assignment was making sure that you understood that assembly process, how each element's value went into the matrix at a particular point. That's really what I was after. Since our recording started, I'll go ahead and just open the floor up again to some general questions. I got a lot of emails about this one homework assignment. So if there are questions, let's ask them now. Any other questions about the assignment? There was one before class, like what if the member codes were switched? Like what it was, like instead of 2424, like if it was switched, and that shouldn't affect your answer at all. Typically we go from lower to higher, but that doesn't really matter very much. But I had some, like, I know there were some students that sent me emails that haven't asked anything yet. So are there any other outstanding questions? That's okay. That's okay. What I want to do today is throw a wrinkle into the mix. And yes, there is. Although this homework is a lot easier. It's a lot easier. I'll admit that last one was challenging. This one's a lot easier, I think. Okay. I want to show you something here on the board real quick. And I'm going to throw a wrinkle into the mix, and you'll see why. So here's the network that we did on the homework assignment, okay? And, well, I tell you what, Mr. Atkins, I'm going to post the solution, and then after the solution, after we've graded it and looked at the solution, maybe I'll post one after that, because let me say this, I think the way I prepped up the solution, it's really easy to interpret, and if there's still any confusion, then I'll be happy to. But I think you'll see what I mean when you look at the solution. Okay, I want to add a wrinkle into the mix. Okay, there was a statement on that homework assignment that was maybe a bit deceptive, but or maybe you glossed over it, but I made it a point to bold it and underline it because of what I'm about to say today. So one of the things I said about each node on that assignment is I said that each node had 1 degree of freedom, okay? And I made it a point to say that. So for instance, here's joint 1, joint 2, joint 3, joint 4, joint 5. I really wanted you to start thinking about problems in terms of degrees of freedom. So if we wanted to just remember, you know, we started out, we assumed degrees of freedom in the x direction. So that's 1, that's 2, that's 3, that's 4, that's 5. So overall, the big old matrix at the end was a 5 by 5. And the reason it was a 5 by 5 is because there was 1, 2, 3, 4, 5 joints, and each joint had 1 degree of freedom. So one way you could look at this is you could say, okay, your big old K matrix, like the size of it, could equal the number of nodes times the number of degrees of freedom per node. Like, does that make sense? Each node only had 1 degree of freedom, and so because it only had 1 degree of freedom, there were 5 nodes. That's why the whole system was 5 by 5. Does that make sense?
Does that mean in the forces in the vertical direction for all those nodes were equal to 0, as were the forces in the negative x direction?
No. All right, so that's 2 different questions. So for this problem, we were not considering anything up or down. So everything up or down didn't matter. So you could say there's 0, whatever, they don't matter. But you just said something. You said, does that mean that all the forces in the negative x direction are 0? No, that's not the case. When I say degrees of freedom, I'm talking about possible forces or displacements in the x direction. So like number 3, okay, positive would be to the right, negative would be to the left, but I'm talking about along a single axis, all right? So yes on the vertical, but no on that to the left, because look at the force vector on that problem. There, like I think it was F5 had a load of -40, so that would be to the left. Did that make sense? Remember, I want you to think about this in terms of degrees of freedom. Forces and displacements acting to the right are positive, to the left are negative.
Okay, I got it.
Is everybody else okay with that? And is everybody okay with that discussion? Okay. Now I'm going to make things complicated. Okay. Now I'm going to make things complicated. What if each joint did not have 1 degree of freedom, but it had 2? Okay. So what would that mean? Okay. Well, it would mean 10 by 10, but let's talk about some physical meaning of that as well. So let's add something physical that I think would make a lot of sense to us. So let's take joint 1. Joint 1 could have a force or displacement in the x direction, but it could also have a force or displacement in the y direction. So this could be 1, 2. This could be 3, 4. This could be 5, 6. This could be 7, 8. This could be 9. This could be 10. So your big old K matrix, as Mr. Roman said, was exactly right. It could be it'd be a 10 by 10. All right. So that's the first thing to keep in mind. The other thing to keep in mind are your member codes, right? So like, for instance, are they always in the same direction? Okay. So when we're talking about degrees of freedom, what I'm indicating here are the positive directions, right? Remember, we always consider forces and displacements to the right are positive, and forces and displacements that are upward are positive. So this is just me indicating the total possible number of unknowns and just showing their positive direction. So like if I had a force, let's say force number 2 was -12 kips. I'd have a vertical load that was 12 kips, and it'd be acting downward because it's negative. Does that make sense?
Okay. So I have a question. Okay, so you couldn't add like an 11th degree of freedom pointing towards the first node, the number 1 node. Well, like going in the negative direction on the right side of that first node. You couldn't add an 11th degree of freedom in there.
Well, what would
in the
that
x direction.
What would that mean? I think the way I would answer that is it would mean, like, we got to talk about what it means, what a degree of freedom even means. A degree of freedom means just a possible force or a possible displacement, right? So I have this point 1. I'm saying it can move along the x-axis. It could move, 1 inch this way. It could move 3 inches this way. It could move 2 inches that way, right? So like this would be 1, this would be 3, this would be -2. you're saying that, well, what about a degree of freedom moving that way? That wouldn't really mean anything, because a degree of freedom moving this way would just be a negative of this value. So there's no, I'm talking about independent unknowns, and a degree of freedom going that way wouldn't be independent. Now, if you want to talk about adding additional degrees of freedom, a degree of freedom has to be an independent quantity. So how about this? Degree of freedom number 1 is in the x direction. Degree of freedom number 2 is in the y direction. If you want to add a third one, how about in the z direction towards the screen? You see what I mean?
Okay, okay. I think I misunderstood something from the lecture that we went over there. I'm sorry.
Think about it like a coordinate system. Like there's an x and y axis. Like, can you add an axis going in the opposite direction? Well, yeah, but it doesn't really do anything, right? Like if you have a coordinate, like a point on a coordinate system, it's defined by its x and y coordinate, right? So you need those two quantities. I'm saying to define the displacement here, you need two quantities. It's displacement in the x direction, it's displacement in the y direction. These arrows are just pointing in the positive directions. Does that make sense? Okay, now a couple things I want to point out. Okay, so first off, okay, as Mr. Roman said, the big old K matrix for the whole system would be 10 by 10. But if I look at the system this way, how big is the stiffness matrix for each member? Before it was 2 by 2. What is it going to be for each member now? 4 by 4, exactly right. Because now I've got additional degrees of freedom. So I've got, like 1, 2. So like each member is going to be 4 by 4. So I got to figure out what's going on inside each one of these members. The other thing I've got to figure out is my assembly. Like for instance, if I'm looking at member number 4, I'm not just looking at 1 to 5. Now I'm looking at the degrees of freedom. So it would be 1, 2, 9, and 10. This would be like 1, 2, 9, and 10. 1, 2, 9, and 10. Does that make sense? See, before we only had 1 degree of freedom on each joint, so we would just look at the joints and say, okay, 1 to 5, okay, 1 to 5. But now, because each joint has a new degree of freedom, we have to look at it in those perspective. So these member codes are not going to come from the joint numbers, but from the degrees of freedom. Does that concept make sense? Okay, all right. And then if you understand that, then there's only one other thing that we've got to, oh, my window dropped down here. Give me 1 second. There's only one other thing that you kind of need to understand in order to attack this problem. And what am I talking about right now? Does it matter how you number that's a great question. Does it matter how you number them? And the short answer is no, not really. You can number them in whatever order you want. And I say that with the caveat that if we really wanted to get hyper specific on computer applications, there are ways to number them that are more efficient for the computer's perspective. But for the problems that we're doing in here, and the fact that we have computers that are so powerful that, you can run Skyrim on your watch nowadays, that, you can number it any way you want. And I don't think any of the computers that we deal with nowadays are going to matter. Unless you get into super huge models, in which case that's another discussion for another day. But the short answer is no, you can number them in whatever order you want. The one thing, though, I will say is you've got to be consistent. See, like when we do an analysis problem in matrix analysis or finite elements, one of the first things we do is draw this. This is our analytical model, and we say, okay, we're going to remain consistent. Like if this is number 9, it's always going to be number 9. If this is number 6, it's always going to be number 6. So that when I assemble, I keep things consistent. Does that make sense?
Yeah, it makes sense. But what I was kind of asking also is, like, does it have to be consistent in the fact of, like, in your X directions, it's 1, 3s, 5, 7s, 9s?
No, it doesn't have to be. It really doesn't have to be. This is just conventionally what we do. Like you could do 1, 2. You could do, 3, 4. It wouldn't matter. But conventionally, we number it in that fashion. Like if you go to Google and you start searching, stiffness matrices for bars and trusses and all this stuff. That's how it's going to number them. So I'm just using the conventional numbering system that everybody used. It's like what we were talking about earlier. Like somebody flipped the coin and that's what we decided. So we just, you know, picked a convention and stuck with it. Okay, good deal. So here's why I'm making this complicated, okay? And then you'll see where we're getting at this. Why am I adding a second degree of freedom? Well, a bar element has 1 degree of freedom per joint, but what do we call an element that has 2 degrees of freedom per joint? We have a name for that element. We call it a truss element. So what I'm talking about is how RISA does a truss analysis, okay? And the only thing that makes it complicated beyond this is trig, okay? If you can do trig, then you can handle this. All we're going to do is take what we did before with bar elements and just add trig to it. That's it. And if you can handle that, that's how RISA does a truss analysis. I'm not going to make you do a full-blown one start to finish, but I do want you to understand the process. So let me go back to the notes here. So let's talk about our flow chart, okay? And so let's go back to this. And what we're going to be talking about today, when I say trig, I'm going to try and explain this whole local and global coordinate thing. And the difference between the local coordinate system and the global coordinate system is trig, okay? But let me just bear with me. So the top blue boxes are, again, everything that we understood before we started this. We knew how to create a model in RISA, and we knew how to report it at the end. Now that we've done a problem and done a homework assignment, let's see if we can digest what's going on in this flow chart. So we assemble the K matrix, right? So we compute a K matrix for each member, and then we assemble it into a K matrix for the whole system. We collect the loads into a global vector, and then we compute the unknown displacements. And how do we do that? We knock out the rows and columns associated with the boundary conditions, invert the K matrix, multiply it by the force vector, boom, those are the displacements. And then we took those displacement vectors, we broke them up into one for each element. F times K delta told us the forces in each element. And that was it. Like, I know that the problem was kind of long, but I want you to think about the process, right? A K matrix, assemble it, assemble your force vector, solve for the displacements, break up your displacements, solve for the forces in each member. And then the other thing I want you to keep in mind is, again, the ground rules, the consistency on your sign convention. X direction is positive, X direction rightward is positive, Y direction upward is positive, okay? Is everybody okay with that? Everybody good? Because this is important. All right, now, let's talk about bar elements versus truss elements. And again, this goes back to the new term of a degree of freedom, okay? So it's the degree of freedom, as we said, it's the total number of possible nodal displacements for a member. So if we go to the bar element had 1 degree of freedom per joint. And so we just said 1 and 2. And so the bar element stiffness matrix was 2 by 2. And so that's what it looked like. This is what we got for the stiffness matrix for a bar element. It was just this right there, okay? And it was just EA over L, EA over L's, because those were the stiffness terms. Now, for the truss element, it's going to be 4 by 4. And so ultimately, we're going to need to figure this out, okay? And it's going to be a little surprising how we get this in the end, but obviously our challenge is to see if we can fill in each of those terms, but that's not the only problem we have to deal with. There's another problem that we have to deal with, and I'll go ahead and tell you, we kind of ignored this problem on the last homework assignment, but now we're going to deal with it. And the problem that we have to deal with is the coordinate system. See, in general, truss elements are oriented any which way they could be, right? I mean, how many truss problems have we done in this class, right? The members are oriented all over the place, right? You could have member going like this, member going like that, member going up and down. And what we need to do is we need to not only derive a stiffness matrix, but we need to derive a stiffness matrix that's with respect to a common coordinate system, so that when we assemble it, we are assembling apples to apples and not apples to oranges. So the way that we handle this is we use the following terminology. So we have the term local coordinate system and global. Now, everybody in this class has already dealt with a global coordinate system, right? So we've done homework problems using RISA. And if you remember, how do you define a RISA model? How do you build the geometry and plot, select the joints and whatnot? Remember, you had to select an origin, right? So we'll say, okay, that joint is 0, 0. And then we define all of the other joints based on that common origin, right? So there's a common origin, a common coordinate system that we apply to the entire system, okay? And that's called the global coordinate system. The local coordinate system is oriented with respect to the element, okay? So if I have an element out in space, the X and Y coordinates would sort of go along with that. And I'm going to show you why we have a local coordinate system. It's actually not to make things complicated. It's actually to make them simple. Okay, let me show you why. This right here is a rubber band. Okay, so this rubber band, I'm holding it like this. Okay, if I take this rubber band and I yank on it, I am stretching it. I am applying an axial displacement. Okay, so here's the rubber band before, here's it after. Here's the thing, okay? The behavior of this rubber band really doesn't matter if I take the rubber band and yank it like this, or if I take the rubber band and I yank it like this, or if I yank it like this, or yank it like this. It doesn't matter. So usually it's easier to define a coordinate system with respect to just the element, because I can define the mechanics of the element a lot easier if I'm just looking at an element at a time. But if I have an element that's sort of oriented like that, I want to assemble that in a big old system. Well, I got to use basically a little bit of trig to get this element that's at an angle, split those terms up into their sines and cosines so that I can assemble it with the whole system. Now, going back to the rubber band, let's talk about the rubber band, because mechanically this rubber band is very similar to a truss element in a roof truss or a bridge truss, because one of the things that we've assumed when we analyze a truss, whether it's in tension or compression or whatever the element is, we always assume that it only has axial stiffness. It only responds axially. Like when you did method of joints or method of sections, there's only an axial load and nothing else, no shears or no moments. So if I take this rubber band, the only way I can, quote unquote, put some oomph into it, store some energy in it, is to load it axially, right? If I take the rubber band and I lift it up or lift it down, like if I do that, there's no response. It's just flimsy. In order to apply stiffness or to apply load to this rubber band, I have to load it axially, okay? So the first thing that we're going to do is we're going to look at this element locally, okay? So here's the element. Here's the element, okay? So we have a local coordinate system and a global coordinate system. Yes.
Those comments that you just made about axial loading, that all that is only, that's unique to trusses, right? But you can load shear in frames.
You are exactly right. And that's like one of the things I said at the beginning, is that we are going to limit our discussion in the class to trusses. See, if you generalize the discussion a bit and you add beams and frames, or beam elements and frame elements, I'll show you here in a little bit how what I'm saying would change if you're talking about beams or frames. And ultimately, you'll be able to see this here in a little bit. So give me a little bit of rope and you'll see why. But I'll be able to easily demonstrate how it'll change. Okay, well, let's go back to bars, right? So I want to start off by looking at the bar locally. Okay, now locally, along the local coordinate system, there are 4 degrees of freedom. But the point I want to make mechanically is that a truss element is no different than a bar element mechanically. The only difference is a truss element is a bar element that can be oriented at different angles. Okay, along the local coordinate system, all a truss element is going to be is just a bar element and nothing else. So if you look here, this is the truss element locally, and I propose that its local stiffness matrix is just this right here. It's just a bar element expressed in a 4x4 matrix, and everything else is 0 because, going back to the rubber band, it has no stiffness axially or other than axial behavior. So its axial stiffness is EA over L, and otherwise its stiffness is 0. So locally, that's the stiffness matrix for a bar. I keep using this term locally because what I'm going to have to do is take this and transform it into a global stiffness matrix. But does this make sense? And the reason why I've got it written like this is 1, 1, 2, 3, 4. 1, 2, 3, 4. 1 and 3 are the ones that are along the axis. Does that make sense? Okay. All right. Now, this is the local stiffness matrix, but this doesn't answer my original question, is what's the global stiffness matrix? Well, I got to rotate this thing, okay? The way I'm going to rotate this is trig, okay? In matrix algebra, we have this term called a rotation matrix or a transformation matrix, and basically it's a way of taking a vector and going from a local coordinate system to a global coordinate system. And so to handle this, we use a transformation matrix, and it's basically just trig. It's just cosines and sines. Now, one of the things that I threw in that flowchart, remember how I said there was like lowercase letters and uppercase letters, and I said it's not an error? Well, it's not an error. One of the ways we do this from a terminology perspective is anytime we use a lowercase letter, we're calling that refers to local coordinates. And anytime we have an uppercase letter, that refers to global coordinates, right? So it's like a Bob Ross, like I pulled a sneaky on you. Anytime you see the lowercase letter, that refers locally, and anytime you see an uppercase letter, that's globally. Now, the way that we formulate this is we take a vector in the local coordinates, we say it equals the transformation matrix times the vector in the global coordinates, and all we have to do is fill those terms in. But I promise it's really easy to derive this. It's just trig, okay? So remember, everything to the right is positive, everything upward is positive. So check this out. So if we focus one node at a time, right? So we take one node at a time and 1 degree of freedom at a time. So if we look locally, so if you look at these two images, this is local degree of freedom 1, this is local degree of freedom 2, right? Okay. Local degree of freedom 1 can be split up into x and y coordinates, right? So the global x and the global y is just g1 times the cosine, g2 times the sine. I'm using the l's and g's for local and global. Over here, this is where you kind of have to pay attention to, because if you look locally and you split that up into x and y, this one goes the other way, right? It goes to the left, right? And forces to the right are positive. So if you look at my equations, you could see that I've got, everything's positive over here, but over here, that term's negative, because if I take that local and I, turn it, perpendicular, that's going to go to the left. Also, the trig functions are flipped because, remember, if you have a perpendicular line, you flip your trig functions. So this is basically, your T matrix, right? Your local 1 is going to be global 1 times the cosine plus global 2 times the sine, and then local 2 is going to be global 1 times the negative sine and global 2 times the cosine. So if I just keep on doing that and write it in matrix form, bam, there's your T matrix. That's it. It's just sines and cosines, okay? And so I just want to make sure that that concept kind of makes sense. So if I wanted to determine local forces, I would take the transformation matrix times global forces. If I wanted local displacements, I would take T times the global displacements. So that's my T matrix. One other really crazy property about T matrices is that they are orthogonal. And if you remember a while back when we talked about matrix algebra, I said, we have symmetric matrices, right? So the matrix equals its transpose. Matrices are not symmetric, right? Because if I take the transpose of that, I get a different matrix. They're not symmetric, but they're orthogonal. The transpose actually equals the inverse. And that's kind of crazy if you think about it. But remember, if you take a matrix and multiply it by its inverse, you get the identity, right? You get ones along the main diagonal, zeros everywhere else. Well, what happens with this, if you multiply it by its transpose along the main diagonal, you get cosine squared plus sine squared. What is the cosine squared plus the sine squared? It's 1. And then everywhere else, you either get zeros or you get sine cosine minus sine cosine. So it ends up equaling 0. So there you go. So this matrix is orthogonal. It's rotation matrices in matrix algebra are orthogonal, and they have a really cool property. They make our life a little easier. Now, here's what I want to show you. Okay, if you wanted to find, if you wanted to find local forces, you take the transformation matrix times global forces. If you wanted to find local displacements, take the transformation matrix times global displacements. But does that mean that the local stiffness matrix equals T times the global stiffness matrix? No, that does not mean that. Okay, and I'm going to show you why. It's really easy. Okay, so here's what happens. So watch this. So this is true. All right, local F equals T times global F. Local delta equals T times global delta. That's easy. But what about the K matrices? Because this is what I'm after. So first off, let's agree with a fact. Let's start off with a fact that we can all agree on. All right, local forces equal local stiffness times local displacements. Everything's local. Okay. Then what I'll do is I'll say, okay, let's take the local forces and replace it with that, right? And then let's take the local displacements and replace it with that, right? So I'll substitute my global vectors. Then what I'll do is I'll multiply both sides by T transpose. Because rotation matrices are orthogonal, T transpose times T cancels out. So over here on the left, I get global, global, and that's my global. So how do I get the global stiffness matrix for a truss element? I take T transpose times K times T. Do you remember on the homework assignment, I think it was homework 8.1, do you remember there was a problem where I said, I gave you all, I think it was like matrix A, B, and C and whatnot, and one of the things I asked you to do was, it was A transpose times B times A. Remember me asking you to do that? I wonder why I asked you to do that. This is why. Because in order to determine the global stiffness matrix for a truss, you do T transpose times K times T. Before I show you a quick example, does this make sense? This is sort of the summary. Okay. Don't worry, I'm not going to make you do a full-blown truss problem. I just want to see if you can do the stiffness matrix. I'm not going to make you do the full-blown thing. So I want to write a global stiffness matrix for a couple of these members. So we'll say each of the members are 29,000 KSI. The cross-sectional members of the areas are shown. Keep in mind, we've done this problem before. And I also tried to number them the way that RISA would number them. So it would do like N1, N2, N3, N4, so that you could kind of see what's going on here. And I'll walk you through this. It's really simple. Okay, so we're going to write the stiffness matrices for two of the members. We're going to use Excel to make our life a little easier, but let's go ahead and see if we can knock this out. All right, so let me stop the share. And let me pull up my notes. Give me one sec. And I'm really going to try and show you how a computer does it, because I think that's the kicker. That's what matters. So bear with me. I should have had this set up before, but I had a lot of stuff to do right before class. All right. So share application. All right. So let me show you how this works, okay? Because this is really simple, and I really want to show you how a computer does it. All right. So first thing that I'm going to do is I'm going to treat this like a RISA problem. Okay. So in a RISA problem, how would you model this? Okay. So we need to pick an origin. Like, what do you think we should pick as the origin? Maybe that one, right? Like, how would you build this in RISA? You'd say, okay, I got 4 joints. I got a model. I got to plug those in and start defining my members, right? So this would sort of like, this would be my x-axis, and that would be my y-axis, right? So this is 0, 0. All right. Now, let's see if somebody's paying attention. What are the coordinates of that point? Okay, 6, 0. All right. Now, one of the things I haven't emphasized on this problem is, no, that's fine, that's fine. But one of the things I haven't emphasized on this problem are units. "72 inches. Make sure to use a consistent unit system when you're doing this, okay? Because that really matters, okay? And this is 6 feet, but you know, all of our E values, so E is 29,000 KSI. All our A values are, you know, in inches squared. All our forces are in kips. So make sure that your coordinates are in inches as well. So I'm going to turn this to 72 inches, turn that to 96 inches. Just do that right now, okay? Because that's easy to mess up. RISA does this internally, okay? So this point right here is going to be 72 inches, 96 inches. This is going to be 0, 96. Is that okay? All right. Okay. Let's look at element N2, N3, right? So let's write down some data that we know about this element. E is 29,000, right? Its A 1.5. Now, I'm going to go through the length calculations a little differently, but later. But does anybody know how long this member is? N2, N3. This is N3. This is N2. I'm talking about that member. Like, how long is it? Not. All right. Hold on. Yeah, it's 120 inches. Wait. How are we getting 122?
I had
So
70 in the calculator, not 72. My bad.
oh, okay. It's fine.
I'm all scatterbrained this morning.
It's fine. It's fine. Now, are you good, Mr. You said 72.
I was confused about which member you were even asking about, so my bad.
No, it's fine. It's fine. Now, I want to show you something. This is how a computer it would do this. So what I want to do is I want to compute the change in X and the change in Y. Okay. Now, the change in X, the way that a computer does it, and again, you just have to sort of pick a convention and go with it, is it's going to take the highest value minus the lowest value. And so we're going from, those are the two joints. So this is going to be X3 minus X2. This is going to be Y3 minus Y2. Okay, and I'm going to show you why we're doing this. So X3 is 0 minus 72, negative 72. This is 96 minus 0, so it's positive 96, right? Does everybody kind of see what I'm doing? So what a computer would do in order to compute the length of a member, it would say that the length is delta x squared plus delta y squared, and it would take the square root and get 120. That's what a computer would do. But here's the other reason why a computer would compute a delta x, delta y. I don't know about you, but the cosine of this angle, whatever the orientation of the member is going to be delta x over L. The sine is going to be delta y over L. Right? I mean, you got a triangle. Here's the angle, delta y, delta x, L. Adjacent over hypotenuse, opposite over hypotenuse, right? So what do we have? Negative 72 over 120, positive 96 over 120. Anybody have an answer for those? All right, hold on. You might want to check your calculator again. Because this should be negative 0.6 even. And this should be positive 0.8. There you go. Right? And while we're at it, one more thing. EA over L. It's okay. All right, I'm getting EA over L of like 161.11, something like that. Everybody else getting that? All right. So, all right. So in order to determine the global stiffness matrix, we need a local stiffness matrix. But that's easy. So here, I'll write it with like kind of a lowercase k. That's easy because remember, it's just EA over L in those 4 cells, right? So this is all it's going to be.
I don't know if I'm doing like a unit conversion wrong or something, but I'm not getting that for EA over L.
Did I not?
I'm not
Hold on.
either, but I didn't want to say anything because I don't trust my calculator.
I
Oh,
got
you're right.
362.5.
You're right. Yeah, you're right. Yep. You're right. Whoops. So yeah, so this is going to be, yeah, you're right. 362.5 minus 362.5, 362.5 minus 362.5. So yeah, so that's your local K matrix. And then your T matrix, this is the new one, equals, whoop. So here's what the T matrix looks like. It's, and I just use little letters because I'm lazy. C S minus SC, and then just that repeated, CS minus SC. And those are the sines and cosines, and those are zeros. So what do we got? We've got negative 0.6, negative 0.8, and then 0.8, negative 0.6, and then just that repeated. So we've got our K matrix, we've got our T matrix, and then all we have to do is plug that into Excel. Just say, you know, T transpose times K times T. Why are there not any negative C? That just comes from the formulation. If you go to the slides, what is it? Here, hold on. I'll do this a little differently. So yeah, that just comes from the derivation. Like when we did our derivation, there just weren't any negative cosine terms. Like they were just all positive. The negative was the sine term. Yeah. So like here's what your matrix looks like, and to CS minus SC, just the C's ended up being positive. And so what we would then do is just plug that into Excel, whatever we get, and then that's our stiffness matrix, right? And then in terms of member codes, right, here's the structure. Typically what we would do is we would say 1, 2, 3, 4, 5, 6, 7, 8. And so we're talking about the diagonals, so it would be 3, 4, 5, 6, 3, 4, 5, 6. And so we would just put those terms into the assembled matrix, and we would just carry on the process. So the point I'm making is that this is the exact same process as before. There's no difference at all. It's just there's an added step, this local to global. That's it. Does that make sense? One final thing I'll say about the homework. I'm giving you two members to do a stiffness matrix for. I'm going to give you a little bit of a hint. I'll probably post on Teams to make it a little easier. Any quick questions before we call it? No, you're fine. You're fine. Well, let me say two things. when we come back from break, the matrix stuff is over. I got, for lack of a better term, I'll have some simpler stuff for you. But I got one more homework assignment. You could probably actually knock it out in the next couple days, but it's pretty short. And with that, I'm not going to see y'all till November 30th. You all take a break. Take it easy. And I will see you all at the end of the month. You all have a wonderful break. When's the 30th? So you could do it. You could probably do it this week, but I'm giving you till when you come back. It's not very long, but it's due on the 30th. And I'll post a little video on Teams probably on Friday to sort of show you like a little shortcut if anybody's interested. All right, everybody. You all have a wonderful break. I will see you all on the 30th. That's all I got, everybody. We'll see you then.